Okay, so I'm going to do the modified Atwood's machine. So the modified Atwood's machine means that it's something that there's one guy hanging down, but the other guy is, instead of hanging down as well, is on a table. And this can be with or without friction. So let's call this guy M2, this guy M1. Okay, so we've got M2G and tension here. Here we have tension, we have M1G, we have Fn, and let's say we have, this is on a rough surface. So you can imagine that for a certain mass of M2, it wouldn't be enough to overcome static friction, and so that would just all be at rest. That was static friction, but let's say this thing is actually on the go, and so this is going to be kinetic friction. So the block on the table, M1, is going to be T minus Fk is M1A, and Fn minus M1G equals 0, right? Because what was this? This was really net force is M1A, and it had 2 dimensions that we had to worry about. The first one I wrote, of course, was the horizontal one, and the second one was the vertical. For M2, we'll get, there's only going to be one dimension, actually, with any forces. And so it's going to be M2G minus T equals M2A. And that's, of course, because I see that A is down, so I look over here and say, which one's down? I start with that, and then subtract the others. Cool. So we have 3 equations. 1, 2, 3. All right. This one is telling us lovely things like Fn equals M1G. And then when we plug that into equation 1, T is mu K Fn is M1A, and Fn, we just said, was M1G. Okay, so now this guy and that guy will give us some good stuff. And you guys seem to be wondering sort of, how do I figure out like how to combine these things? If I want to solve for this acceleration, I want to get rid of T. When I'm looking here, I'm seeing that one of my equations has a minus T in it, and the other one has a positive T. So if I add them, I know it'll go away, right? So if you call this equation 4, I'm going to add 3 plus 4. Okay, so the left-hand side, and you can do it this way, M2G minus T, add that left-hand side, plus T minus mu K M1G, and then we add the right sides, and it's M1 plus M2A. My T's go away, and I get this lovely result. And as always, when I get a result, I want to look at the limiting cases. So what interesting thing happens when there's no friction? If there's no friction, I get A is M2 over M1 plus M2. Oopsies, I forgot my parentheses here, guys. My bad. I was like, this isn't going to work. Where's my G? So there's my G. And this, of course, is just that's the result of a half-Atwood's machine with no friction, right? Because it's only that weight of M2 that is providing that acceleration, and you've got that total inertia of M1 plus M2 resisting you. Okay, what happens if M2 is greater, much, much greater than M1? Then you get M2 over M2, which is G So that should make sense. But what happens if M1 is, I wrote the same thing again. I literally always do that. What if M1 is actually much, much greater? Well, you're thinking, okay, it's not going to move, right? Yeah, you're right. Mathematically, you know, you get this, like, you get negative G. But you're like, that doesn't make any sense. What, is it actually going the other way? No. And it's because when we wrote these, there was the actual assumption that it was already moving, and therefore it was kinetic friction. Okay? So the actual interesting question is, right, what mass does M2 have to be for this thing to actually start moving? And so you can see it's that critical thing right there. So M2 has to be greater than or equal to mu K M1. Actually, mu S M1, I'm sorry. M2 has to be greater than mu S M1 in order to start moving, because if we're interested in that particular situation to actually get it to move. But you can see sort of mathematically that the mu's take on the same placement. So anyway, that was a half Atwood's machine. Hope that helped.